Hello, this is the lecture for section 2.1, linear functions. Let's start with a definition of a linear function. A linear function is any function where the rate of change is constant. Right? The rate of change is constant. In fact, another way of thinking about the rate of change for a linear function is that it is the slope of the function. Right? The graph of a linear function is going to be a straight line. So when we graph a linear function, we really only need 2 points on that line to graph it, right? And the most valuable, maybe, or common form for the linear equation, the function form for the linear equation is f of x equals mx plus b, where m is the slope of that linear function, or the rate of change, right? Slope, or the rate of change of the linear function. X, of course, is your independent variable, and B is your, on the graph, B is going to be your vertical intercept, or y-intercept. Or we might think about this as the starting point or initial value of the function. Okay? Some more specifics on the slope or the rate of change of a linear function. It would be increasing, the rate of change is increasing if the slope is positive. Of course, when we graph a line with positive slope, as we move left to right across that line, it's going to be moving upwards. All right? If the function is decreasing, then the slope would be negative, or when we graph that line, we move left to right across that line, it's going to be moving downward. All right? There's algebraically, there's several ways we can think about the slope. We usually refer to it as m. If we're looking at a graph, we might think of the slope as rise over run. Okay, so we get from one point to another point. What do I have to rise, or how much do I have to move up? And then over run, the denominator would be how many units would I have to move either right or left. Up is going to be positive. Right is going to be positive. Down would be negative. Left would be negative. Right, so this little example here, I said I moved up 1, 2, 3, and I move to the right 1, 2, 3, 4. So the slope of this line might be 3/4 when you think about it as rise over run. I can also think of the slope as the change in y coordinates of points on the graph. Delta, that's the Greek letter delta. We use that to refer to as change in mathematics. I could also think about the slope as the change in y over the change in x. All right, same kind of thing here, rise over run, change in y, we go up or we go down, right? Or change in x, we go right or we go left. All right, as a formula, I could write the slope as y2 minus y1 over x2 minus x1, where y1 and x1 are coordinates of 1 point on the line, on the graph, right? And x2, y2 are coordinates of a second point that's either on that graph, or we can even think about this x1 and y1 as a set of ordered pairs that satisfies the equation, right? Makes it true. And x2, y2 as another set of ordered pairs. And then one final way to think about the slope or the rate of change of a linear function is f of x2 minus f of x1 over x2 minus x1. This is simply saying the output of the function when x2 is my input minus the output of the function when x1 is my input, right? Or another way to think about f of x2 and f of x1 is that they're just function notation for the y's, right? So f of x2 can be thought of as y2, f of x1 can be thought of as y1. All right, so hopefully this is all feeling like review to you. It's all just different ways to think about rate of change. Let's look at an example now of creating a linear function in its most common form. right? So as a function, we always have to have all equations solved for y, right? And we all know the equation y equals mx plus b. It's kind of our standard form for linear functions, right? As a function, we would say f of x equals mx plus b. And again, m here is your slope or rate of change. And then b, it's your y-intercept or your initial value. All right, so here we have a situation. Suppose we're running a coffee stand. Labor costs $90 per day, whether you work there yourself or if you hire somebody, you pay that person $90 a day. Okay, and then the per cup of coffee costs $1.30. So that's the cost of the cup itself, the coffee beans, and anything that goes in, any condiments that go in that coffee, right? $1.30 per cup. All right, so if we want to write an equation for the daily cost, that's like we're writing a function for the daily cost, right? We might call that function C, right, for cost. So let's see. And it's going to be a function of what? It's going to be a function of the input. What is the input going to be here? Well, let's think about this for a minute. If linear functions are set up so that they're the rate of change times the input or independent variable, plus the initial value, we would probably have to identify, we've got a couple numbers here, the $1.30 and the $90 per day, which would be the input, which what role in the linear function do these values play? All right, well, let's see, what would the rate of change be here? Well, every time I sell a cup of coffee, I will incur the cost of that coffee, right? That's $1.30. Every time I sell one cup of coffee, though, it doesn't change my labor cost. The labor cost is sort of all day. Okay, so it looks to me like this $1.30 is my rate of change, right, or my slope. Okay. Now what about the $90 per day? Well, if I don't sell any coffee at all, do I still have to pay the person that is manning the coffee stand? Yeah, I mean, if they're going to be there, you got to pay them to be there, right? So it looks to me like this $90 per day is sort of my initial cost or my initial value. So given that, what would my function be? Well, let's call this function C for cost. And then what would the input be? What is the independent variable? How does this cost change? It changes as a function of what? Let X be that independent variable. Let's describe it, though. Well, the thing that changes, the thing that's making the cost go up is how many cups of coffee I sell. So we'll let X be the number of cups sold, right? So cost as a function of the number of cups sold is going to be the rate of change, right? Rate of change, that's $1.30. Times my independent variable, how many cups I'm going to sell, right, X. Then plus the initial value, well, I've got that $90 per day cost that I have to incur no matter what, right? So there we have a function to determine the daily cost for running the coffee stand. Let's look at creating a linear function a different way. Suppose I have some function, it doesn't really matter. We don't know anything about it at this point, but we do know some inputs and outputs of this function. All right? We do know that f of 3 equals 5 and that f of negative 2 equals 7. Right? So what does this mean? This means that when we input 3 to the function, we get 5 out. Right? Or there's an ordered pair that would satisfy that function. Right? The ordered pair, if the input was x, which it is going to be here, the ordered pair would be 3, 5. When we input 3, we get 5 out. Or when x is 3, y is 5. Here's another f of negative 2 equals 7, I can get another ordered pair there. I can say that when x is negative 2, y is 7. Okay, so now I have two ordered pairs. If I were to graph this, they would be the coordinates of 2 points on that line. I don't really need to graph this, though, to find the equation here. I can consider one of these points, point 1, and the other one, point 2. So then I'll say, let's say this ordered pair 3, 5 is going to be my x1 and my y1. Okay, and then this negative 2, 7 will be my second point. So negative 2 will be my x2, and 7 will be my y2. All right, so what is that telling me there? Well, I can find my rate of change here, or my slope, right? I can find it using the equation y2 minus y1 over x2 minus x1. Right? So this rate of change, or this slope, it's going to be 7 minus 5 over negative 2 minus 3. Well, what does that simplify to? 2 over negative 5, or we might call that negative 2/5. Okay? That's my rate of change. Right? So every time the x increases by 5, the y decreases by 2. Or every time the y decreases by, or the x decreases by 5, the y increases by 2. The ways to think about that. All right, so if I want to find this equation, say in my standard form, y equals mx plus b, I now know what m is. It's negative 2/5, right? So I can say y equals negative 2/5 x plus b. Okay, so I've got part of this equation, right? I just don't know what that initial value or that y-intercept is going to be. So how might I find that? Well, I do know 2 points that satisfy the equation. I know 2 ordered pairs here that would make this equation true. So let's choose one of them. I think I'll just use that first one. Let me substitute 3 and 5 in for x and y. So I'll say 5 equals negative 2/5 times x, what was x? 3, then plus b, and I'll be able to solve for b, right? So 5 equals negative 2 times 3, that's going to be negative 6/5 plus b. So b then, if I add 6/5 to both sides, okay, b then is going to equal 5 plus 6/5. Well, let's see, I should probably add those two. So 5, well, that's like a 5 over 1. Let me convert that over to fifths. So let me multiply by 5 over 5. So b then is going to be equal to 25/5 plus 6/5, or 31/5. Right? So there's my equation then. In function form, or function notation, f of x equals m, which was negative 2/5, x plus b, which I now know is 31/5. Okay? Let's look at creating linear functions one more way. All right? Here we have a town's population that's been growing linearly. Okay, so we have linear growth, right? Linear growth. That means right in my mind, I know that when I graph this, it's going to be an upward sloping line. Linear growth. All right. In 2002, the population of the town was 51,000. And in 2005, that population had grown to 55,000. Right? So we want to write a function, we want to call it P of t, to represent the population of this town. And look at this, t years after 2002. Right? Why do I want to say it's t years after 2002? Would it make any sense to write a function and use an actual year as the input? Not really, because years are kind of funny. They are numbers, but what do they measure? They measure the distance from year 0, and that's very rarely something that's valuable in terms of a function, right? So we're saying our model begins, or maybe the first data we collected to make this model began in the year 2002. Okay, so t, the input to our model, right? So P of t, it's going to be the number of years after 2002. All right, so what do I know? What do I know about this function, and what do I know about this story here, this situation, that I can interpret to data that I can somehow develop a model from? Well, I do know the population in 2 different years, right? So look, in the year 2002, the population was 51,000. But I don't want to make that an ordered pair because years are weird. I'm saying it's years after 2002. So I actually have an ordered pair here that I could call 0, 51,000. Right? I also know that by the year 2005, this population, maybe I should do a narrative, this population had grown to 55,500. Okay. So I might be able to write a second ordered pair here. 2005 is how many years after 2002? It's 3 years, right? 2005 minus 2002 is 3. So a second ordered pair might be 3 and then 55,500. So this now is looking similar to the other one we just solved, isn't it? So I could do the same exact thing I did when solving this problem here, or if I'm thinking, I might be able to do this one a little bit more quickly. Look, the input is years after 2002. Here the input is 0. So what is it telling me that 51,000 is? That's my initial value for this particular model, isn't it? Or in the standard form of a linear function, mx plus b, 51,000 is the b. So I might have just an easier start of it here. I might know what b is already. But do I know the slope or the rate of change? No, but I can find that easy enough, can't I? Let's do it. Slope is the change in the outputs over the change in the inputs, right? Or, let's see, we'll let this be my 0.1. So we'll let my x1 and my y1, my x2 and my y2. So I want to say y2 minus y1 is 55,500 minus the 51,000 all over x2. That's 3 minus 0. Okay, so is that going to simplify to? Let's see, that's going to be 4,500 over 3, or 1,500. Now I have everything I need to plug into my model. Function, I wrote f. It's p this time. We want p of t. P of t, let's try again. There we go. P of t is going to be equal to my slope, which I just found, 4,500 over 3, or simplified down to 1,500 over 1, or just 1,500 times the input. We're using t as our input here, so 1,500 t, and then plus this initial value. Well, this model begins, according to this last phrase here, in the year 2002, so we want to say plus 51,000. Great. Well, that ends the lecture for section 2.1, linear functions.